under your mattress to measure. It's going to put out electromagnetic.
Yeah, g'day, Charlie ZL2 CTM. Just doing some initial checks here as a direct conversion receiver. At the moment, just using the radio over here as a dummy load, or in terms of transmitting into a dummy load and then just detecting it. Later on, when the sun starts to go down, we get the grey line. I'll flash it up again on the proper antenna, but it's working really well actually. So just want to spend this video looking at the VFO. There were some requests for that, so we'll look at the configuration of the VFO as well as looking at the software, just a quick flick through the software. And the other thing I wanted to look at was the bandpass filter. So it's got a very simple bandpass filter there, double tuned between the antenna and the RF amp. Just debating if I want to have it in this configuration or go with what I have done quite a few times now and have it the other way around, whereas I amplify everything coming in on the antenna and then the output of the RF amp goes through the bandpass filter. In that configuration, it's quite easy then through some switching to share the bandpass filter for both the receive and for the transmit circuitry. The flip side is you just build another bandpass filter, but at the moment that's the configuration coming in through the filter through the amplifier. At the moment it's going into, if I can just zoom up on that, that is the ADE-1, so those are those ADE-1s that I wanted to try from AliExpress, and this particular batch, so I've got 4 of them, seems to work perfectly fine. So these are 7 dBm devices, so essentially the same drive levels required as the SBL1, and like I say, that's working really well. So the configuration for that is it's a 6-pin device. The top left hand corner is a ground, IF comes out on pin 2, you throw RF into pin 3, which is the red wire there, 4 and 5 are grounded through that little link, and then pin 6 is the VFO, which is the second red wire which goes through to the SI5351. But like I say, that's working really well, and later on, once, like I say, the grey line comes in, I'll flash it up and do some recording with the actual antenna plugged in. So for now, let's just take a look at the VFO. Like I say, there were some requests for that one. Very simple arrangement. I think that probably the easiest way here would be to zoom back out and we'll look at the schematic. I think would be the easiest way for that. So the SI5351 and the LCD are both I2C devices. So both of those have a 5 volt input, a ground, an SDA and SCL, so the data and the clock. And in terms of the actual Nano itself, the only pins we're going to play around with are A4 and A5 from an IC2 point of view. So A4 is SDA and A5 is the SCL. And as you can see here, those data lines and the clock lines are paralleled up between the SI5351 and the LCD. In terms of 5 volts and ground goes straight through to the Nano's ground, and the 5 volts for both those devices there gets connected directly to the 5 volt pin of the Nano. So the 5 volt pin, I should say, is the output of the internal voltage regulator. But what it does also allow you to do, and which I typically do, is just use an external voltage regulator providing 5 volts into pin 5 as well as anything else hanging off it, and that seems to work well. The only other component required for the VFO is in the setup is the rotary encoder. The rotary encoder typically has 3 pins on one side and 2 pins on the other. Okay, so if we just start off with the 3-pin side, the middle one goes to earth, and then the 2 outer ones go through to the Arduino. Now, the software which we'll look at later on uses interrupts, so we need to make sure that we're connected to the interrupt pins on the Arduino. And for the Nano, that's pin 2 and pin 3, digital pin 2, digital pin 3, not to be confused with the analog pins which I've annotated there with A. So digital pins 2 and 3. The other side of the rotary encoder, those 2 pins is a switch. So when you push the rotary encoder switch down, it makes the switch. So this is a normally open switch here. So one side I just ground, and the other side then goes through to, in this particular case I've just chosen digital pin 9 because it aligns nicely with where I've got the rotary encoder on the circuit board. I mentioned in the software my preference for providing a switched input to Arduino is to switch in a low. So I have the internal pull-up resistor enabled, so pulling up the port to logic level 1 or 5 volts, and then I apply a ground to switch it, and then I have the software detecting, looking for a low. Like I say, that's just the way I like to do it. Just mentioning again here for the Nano, the interrupt pins are digital pin 2 and digital pin 3. So interrupt 0 and interrupt 1 respectively. The IC2 addresses, or I2C addresses, the SI5351, and we'll look at that in the software, is already encoded into Jason Mildrum's library, so there's no need to play around with that one. However, you may need to, and again, we'll see that in the software, change the LCD's address that the data is looking for. So remember, because these are paralleled up, these have unique addresses that the Arduino uses. So it will send a command to a device with an address X, for example, and an address Y. So like I say, for the LCD, I've had for the longest time LCDs which were 3F was the address, but this particular one turned out to be 27. That's quite a common address, that one there, and in the end in fact I just flashed up the I2C scanner, which I've talked about in the code, where you can load that into the Arduino. It'll scan the A4 pin, looking to see what devices are hanging off it, and then that gets reported back through to the IDE through the serial monitor. Now the other thing I made a note here, refer to the Solder Smoke podcast. If you go to the Solder Smoke podcast, or in fact if you go to Google and then Google Solder Smoke podcast square wave and say mixer, it should take you to an article that was published probably going on about 2 years now, which talks about square wave oscillators and their performance when used, as we've seen here, a square wave output going into a mixer. And it's a good article, and the flip side is it basically says that square waves are good for these simple diode type mixers. It sort of slams them on and off in a nice good switching way. So if you're sort of questioning why there's no filtering the output of this clock generator, which the SI5351 is, then I encourage you to go and have a look at that particular podcast to get a good rundown of why that's the case. Right, so the next thing I wanted to look at was the, and like I say, before I go into the filter, after this segment here I'll look at the code, and then later on, once the sun goes down or starts to go down and the signals start to come in, we'll have a look at some on-ear performance as a direct conversion receiver here, which is purely just for testing the filter, the amplifier, testing the VFO, and testing the audio amplifier. So very simple arrangement just to make sure everything's all hunky-dory, and then we can now start to build in there the crystal filter, add in the second mixer, the 2 IF amps, and continue. But like I say, I do this quite often just to do a direct conversion first. Anyway, right, so back to the bandpass filter there. I might do something different next time, but for this particular time, I've sort of just called back on the solid state design for the radio amateur from the American Radio Relay League publication. In Appendix 2 it describes some some filters using what they describe here as the pre-distorted Butterworth tables. So reminding you, Butterworth is maximally flat response. Unfortunately, I couldn't find the calculations they use for doing this online. If I could, then I would have included them here. But because I couldn't, I really do need to not acknowledge, but certainly abide by the copyright markings on that particular publication. So I can't reproduce the calculations. But I don't see any problems actually just reproducing the filter itself. So this is the filter here. So 2 tuned circuits. We got a couple of end capacitors there, which are doing impedance transformation for our 50 ohms. So this is a 50 ohm input and output particular filter here. So working through the design talks about an inductor for this. This is a 40 meter bandpass filter. Talks about 20 turns on a T68-6, so that's the yellow core, using number 22 gauge wire, and that turns out to be 1.88 microhenries. I, for something different this time, elected to use the smaller toroids, so I use the T50-6. So again, using the a really good online calculator, 1.88 microhenries using a T56. Let's say again a T50-6 core is going to require 22 turns, and I've elected to use, in fact I've actually noted down there 26, but if I recall it was actually 24 gauge I used in the end. Right, so that's the 2 inductors there. There's a coupling capacitor in the middle, so that's C12 as they call it, 7.2 picofarads. I had in the junk box an 8 picofarad capacitor, so I just used that one. I'll probably need to buy a few more of those and build up the stocks again. Now the capacitor in parallel with the inductor turns out to be 181.6 picofarads. So I'm going to use for testing a 180 picofarad fixed capacitor in parallel with a 30 picofarad trim capacitor. So that's what I'll use there. And right, so that is the overall configuration of that particular filter. What I elected to do for tuning, and I should go back, this is designed for 7 to 7.3 megs. So what I did for tuning is I threw into the input a 7.1, so halfway through the 40 meter band, a 7.1 megahertz signal. I scoped the output and I adjusted the 2 trim caps for maximum gain, so to speak, or maximum response is probably a better term. Now I've mentioned this before and I'm going to mention it again because it is important. Right, so imagine, so I want to talk about these trim caps here. A trim cap essentially looks like this. So if you look down there you can see the plates. So at the moment the plates are starting to mesh, and at this point in here, with the plates fully meshed, this is at maximum capacitance. And if we go to the fully unmeshed position, this now is at minimum capacitance. So it's important to note that when you're adjusting the trim caps, that when you go through a full 360 degree rotation, you should see 2 peaks. If you don't see 2 peaks and you only get to a point over 360 degrees of 1 peak, then you either have too little or too much capacitance in parallel with the trimmer. And the way you work it out is, if you say over here, which is half meshed, and as you're moving towards fully, say, unmeshed, and it's growing, the peak response is growing and growing and growing, you go through minimum and back down the other side and it starts to decrease, then you can see there that you've got too much capacitance in parallel. So why do I say that? Because as you're moving towards having less capacitance overall, those 2 parallel capacitors, the output is growing. So you could then say remove that 180 and put in say a 150 picofarad capacitor and try it again. If, however, it's the other way around, let's say you're half meshed there, and you're starting to move towards maximum capacitance, and it's growing and it's growing and it's growing, you go through max, and then it starts to decrease again all the way around, then clearly, well not clearly, you have not enough capacitance. So if this was the example here, then I would increase it up to the next standard value and try again. So like I say, the key is you want to have for a 360-degree rotation at least 2 peaks. Well, you can only get 2 peaks, and it'll be on either side of max and min. So somewhere over here and somewhere over here will be a peak. Why is that? Because the capacitance value on this side is exactly the same capacitance value on the other side. Right, that's all I want to say about that. I'll pause here and come back later on and just do a quick, say, minute or so sticky peeking in on the 40 meter band in this fixed test direct conversion configuration. Okay, we'll see you soon. Okay, let's take a quick look at the software here. So this is just the bare bones software with just enough functionality to get the VFO and the beat frequency oscillators coming out of the SI5351. At this stage, no additional functionality has been added in. For example, the selection of upper or lower sideband, or say memories, etc. So like I say, just the bare bones, but should be enough to get an idea of what's going on. Got the includes there. I'll just mention here the SI5351. I'm using Jason Mildrum's library, which I've been using for a long time and works well. Moving down into some global constants here, or variables I should say. In this particular case, we have a band start set at 7 megahertz because that's the start of the 40 meter band. Band end 7.3 megs, and then the whole VFO initializes at 7.1 megahertz. If you were to change these to any other figure, then as you were changing the frequency, that would be the limits of what this can tune to. So you could quite easily make this a broadcast band, or say an all of HF general coverage receiver. But of course you need to verify, change your filters coming in the input. Right, so like I say, I was going to keep this sort of highish level at this stage of the game. Radix, that's used to increment the frequency by a certain amount, and at the moment that's defaulting to 1 kilohertz or 1000 hertz. That's the BFO frequency. This one will be updated once I get the crystal into the circuit, the crystal filter that is, and then work out whereabouts that BFO needs to sit on the correct side of the pass band. So it'll be 300 hertz beyond the minus 3 dB point of that particular filter. So that'll be changed in due course. As per the wiring diagram, you can see there the assignments for the push pins. So this is for the rotary encoder. So the push pins coming in on digital pin 9, and then the 2 rotary encoder pins, pins 2 and pins 3, digital pins that is. Noting that they are the 2 interrupt pins. Now, for whatever reason, if you get them back to front and you're trying to increase the frequency and it decreases, and vice versa, then it's just a matter of swapping these 2 around here. So you can make that 3 and make that 2. So that makes it nice and easy. Instantiating the objects here, so this is where we actually create our objects for both the crystal display and the synthesizer, or the DDS. And that's where I mentioned the address. So this particular LCD that I'm using in this one happens to have an address of 27 octal, and previously it's been 3 Foxtrot or 3F. Now in the, if I recall, if I go to, you can get a I2C scanner. I do have a copy here, which you can then load up into your Arduino, or the Nano in this particular case, run it, and then it will report into the serial monitor screen, which is, I don't have running at the moment, what addresses it finds hanging off the I2C bus. So when I did that, it confirmed that I had 27 as the address I required for the liquid crystal display. Stock standard sort of setup here to setting up those pins. So we're setting up the digital pins to be inputs, and we're writing them high. My preference for switches is to switch a low input. So by setting these high, the internal pull-up resistor is enabled, and then by applying an earth, it obviously creates a digital or logic level 0, which is then sensed later on, which we'll see in the loop. Setting up the two interrupt service routines here, calling upon those two interrupt pins, namely 3 and 2 in this particular case. Right, also in the setup is initializing the display, so turning it on, getting the backlight up and running, running away and actually updating the display, which we'll see further down the bottom, in other words displaying the current frequency, the radix, as well as any name or whatever else you want to put on that one. Here we are initializing the SI5351. What's to note here? Right, so this is an interesting one here. So the drive level 8 milliamps. Other choices are 4 milliamps and 2 milliamps. At the moment, I'm driving a 7 dBm mixer, so having 8 milliamps is appropriate. If you were using, say, a lower level mixer, so you wouldn't want to tempt or to potentially burn that out, so you drop that down to say 2 or 4. Start with 2, give that a go, and then look at 4. And then just turning on the two clocks. So clock 0 will be the variable frequency, so frequency will be changing there, and then clock 2 will be the beat frequency. So just romping through the loop here. So the loop's just always checking to see by going to get the frequency if the frequency has changed from what the current frequency is, and if it has changed, then it updates the display. It updates the frequency, in other words, what the SI5351 is putting out, and then just writes over itself so it can check next time. Here goes that what I mentioned before about what I prefer to like is to apply a logic level low for digital pins coming in where I've applied a switch. So here's a digital read, the push pin, that's the rotary push pin, looking for a low. What else we got here? So that was that get frequency that's been called from the main loop. That's an interrupt friendly call, and then the two interrupt service routines here that are looking at pins 2 and 3 to see if those two interrupts have been activated by the rotary encoder, and then those in turn will call another sub-function called update rot or rotary encoder, and here's that one here. I won't go into this. I obtained this many moons ago, and I like it. It doesn't require any additional library to read it, and for me it works well. But as we can see here, here we depending on if the push button switch has been pushed, and if it is low, then whatever you're fiddling or whatever you're doing with regards to the frequency selector is modifying the radix, otherwise it's modifying the frequency. So you can see here this is the incrementing side, so we're moving our frequency selector in a clockwise direction. Frequency equals frequency plus radix. Now if it gets to the end, band end, and if you recall from the very top, for this 40 meter radio with 7.3 megs, then it stops, it doesn't go any further. Same logic in the anti-clockwise direction, but in this particular case we're now going down. So we're decrementing the radix by a factor of 10, or if the push button switch is not selected, it is decreasing the frequency by the amount of radix until it gets down to the band start, or 7 megahertz in this particular case, and doesn't go any further. And then all that leaves there is two more functions. One updates the display, so that's just in fact that's no longer required. I'll just blank that one out. Just saved a little bit of flickering, so I can delete that one out. writes the frequency. Next line down just puts my name, whatever you want to put there, and then to the right of the frequency, depending on what radix selection there is, it just prints out what the current increment is, either 1 Hz, 10 Hz, 100 Hz, 1K, and the like. So just a very simple routine there for updating the LCD. If you were to move to, say, a 320 by 240 type display, then obviously this whole area here would change, and as they say, the world's your oyster, and you could have whatever you want displayed in it. But for the intent of this particular radio, which is to keep things simple, just to go through sort of the building blocks, so to speak, it's a very simple display. And then the very last one, that send frequency, that's the function that's called from the main loop should the current frequency differ from what the old frequency was. And as we can see here, it just updates clock 0 to be the new frequency, and then not actually required, but I do it anyway. I just reaffirm that I want clock 2 to be outputting the BFO frequency, and that's it. There is really nothing else at all in regards to the software side of this pretty simple VFO. Okay, I'll leave it there and we'll continue. Cheers all.
Because of the noise, it's pissed me off. I've turned all the amplification off, and it does help.
Oh, doesn't sound too bad.
It keeps the noise down to within normal levels, I suppose. But anyway, Bill, really good to hear you. I guess I'm on at the moment that doesn't do very much for my health, unfortunately. It's supposed to, I've got rheumatoid arthritis and have had for quite a...
Okay, that's actually sounding quite good, actually. Just put the antenna on to dummy load. So it's basically no antenna at all. Back on the antenna.
But it's very, very quick acting, apparently. The side effect is it makes my back itch.
Yeah, so that's good. So I won't sticky beak too much onto that one. Hey, just a reminder too, when you're making up these VFOs, what you do need to also do is do a calibration. Now, when I first hooked up this SI5351, it was off by around 200 Hertz. So you'll see that number there, 31830. What you need to do, and I'll just see if I can bring it up, is you need to run a calibration program, and I'll just bring you across to the computer and I'll show you the program that you need to run. So apologies for all the reflections there. If you go up into the library for this particular SI5351 library, so we go into, so I've brought up in fact, this is just any old program, it doesn't really matter. If we go to File, Examples, and then go to, where is it, SI5351 JSON. So I'm using Jason's, Jason Mildrum's library. He has a program here called Calibration. And what you do is you load that up into your Arduino. You then, it'll then set the attached SI5351 to 10 megahertz, and then you basically have a frequency counter, or if you check that video I've done a couple of months back, I use the X and Y channels of the scope, and you can, through using the keypad, you can calibrate it, and then that ends up, it'll print it on the screen, it'll end up with a number, and then what you need to do with that number then is, if we go back into radios, 40 meter rig, you then need to, once you've come up with that number, here it is here. So we're now into the section which is the setup section for the program, and you can see here under initialize the DDS a new line called SI53.set correction, and there goes that number 31830. So that's the number I came up with before when I ran the calibration program, and that's the number I now put back into my normal program as a correction factor. So something to remember when you're using the SI5351 in this particular configuration. Okay, so I'm pretty happy with that now.
Almost the same thing, really. Just causes...
That's basically proven that, well, as far as I'm pretty happy that the bandpass filter seems to be working, the RF amp is working fine, that AD-1 is working well too, which is good. Obviously the AF amplifier is working fine, and as well as the VFO. So at this stage of the game I'm going to pull everything apart again and start to work on the 1350, the IF amps. And I'm sort of inclined now, I'm thinking about having one on either side of the crystal filter. The one on the antenna side will be fixed with a trim pot, its gain, and I think the one on the right hand side will have a control which will allow to change the gain of that, so essentially a manual AGC, and then as a stretch goal for the radio, once it's built, is then to fold back into it an AGC to go into that same input of that particular amplifier. So that's what I'm currently thinking, and we'll just see how well that AD-1 performs as the product detector, and we'll go from there. Otherwise, I'm happy with that. That seems to be working well. So I'll say 73's here. Hopefully this was of use, and we will continue building this radio. Cheers all.